Hi. So our final topic to discuss during this lecture is heteroscedasticity. As you should remember, heteroscedasticity refers to situation when variance of the error term is not constant. So it's depicted schematically on this graph when you have Gini coefficient on vertical axis and predicted value of Gini coefficient on horizontal axis. So you can see there is relatively small value of dispersion here, and then it starts to increase. So this indicates that variance is not constant. You might wonder what might be the possible reasons for heteroscedasticity, and one of them is specification bias. As you remember, specification bias is when you do not include an important variable to the regression model. Consider the following example. You would like to estimate quantity demanded based on price. Quantity demanded for ice cream based on price of ice cream, to be more precise. So yeah, price is important, definitely, and there should be a negative relationship between those variables, but look what will happen if you forget to include seasonal dummy to your model. Regardless of the price, quantity demanded for ice cream is always bigger in summer than in winter. Then again, it increases and decreases. So actually this might result in both autocorrelation and heteroscedasticity. We will get back to this, but that's why when you indicate heteroscedasticity, in your model, it's a good idea to check whether you included all the important variables. Another reason is wrong functional form of the model. So, you remember we discussed Kuznets curve. The relationship between inequality and income per capita can be described by inverted U-shaped curve. So, most closely, this trend can be depicted by inverted parabola. That's why you shall rather choose polynomial regression model. So if you still specify the model as the linear model, you might end up with something like this. So this will result in both autocorrelation, because take a look, the value of residual will decrease and decrease and decrease and decrease. So there will be negative autocorrelation, and heteroscedasticity, because the variance will not be constant. So the next question is how to detect heteroscedasticity. So you have to run the regression model. I will estimate unemployment depending on CPI. Again, I'm doing this on purpose. This model is not good. I'm aware of this. Then you click tests, heteroscedasticity, and let's try Broch-Pagan test for heteroscedasticity. So here you have the output. Zero hypothesis of this test states that error term is homoscedastic, and alternative hypothesis is that error term is heteroscedastic. In our case, unfortunately, we have to reject zero hypothesis in favor of alternative hypothesis. So yeah, this model is definitely biased by heteroscedasticity. So you might wonder what might be the problem about this. And I will tell you. So you can see that in this model, all the variables are highly statistically significant. And this is the main trap. When heteroscedasticity and or autocorrelation are present in the model, they affect the value of standard errors. And t-ratio and p-value consequently. So that's why probably you will end up with variables which are highly statistically significant, but this will not be true. So that's why checking your model for heteroscedasticity and autocorrelation is required. So this is something you have to do before you analyze the output of the model. So first you run pre-estimation tests. You check distribution of the variables, and for time series and panel data, you also check for unit root. After you estimate your model, you check up for autocorrelation and you check for heteroscedasticity. So what to do if there is autocorrelation? First of all, you check for unit root. If data are non-stationary, then you transform into the first difference. Then you have to reconsider your variables. If you specify flow variable as the dependent variable, for instance inflation or GDP growth or anything like this, you have to make sure that independent variables are also flow variables. You might reconsider the choice of variables. Make sure that you add all the potentially important variables and you avoided specification bias. You might reconsider the functional form. And if nothing helps, then you can run GLS model. For heteroscedasticity, it's very similar, except for you might also try to logarithmize your variables, because sometimes skewness serves as the source of heteroscedasticity. So the final thing I would like to show you is how it's actually possible to obtain a better model by doing all of those steps. So on this graph, I estimated unemployment against CPI price level, and you can definitely see that this regression model is not good. First of all, economic theory tells you that there should be a negative relationship between those variables, not the positive one. And second, autocorrelation is definitely the case. Sorry. Okay, here it is. So on this graph, I estimated the log difference of unemployment against the log difference of CPI. It's not precise measure, but something like percentage change in unemployment versus percentage change in CPI. And you can see that this model is so much better. First of all, finally, there is a negative relationship between those variables, just as we should expect. And second, you can see that residuals are much smaller and they are concentrated very closely to the regression line. So yeah, actually all of those recommendations work. And I really hope you enjoyed this video, or at least it was helpful, and see you during the next lecture.